Okay, so these problems are always kind of artificial. I remember when I took this class, this always bothered me. dy and dx, like in this last video, I just talked a lot about dy and dx. These are infinitesimally small. We took a limit. These are essentially zero. dy and dx are essentially zero. We took a limit as delta x goes to zero. And then you're going to have a bunch of problems that tell you to plug in a value for dx. What we're doing is using the differential to approximate changes in function value. So like this equal sign is not a real equal. It's saying write down your differential, and then instead of taking the limit as delta x goes to zero, we're going to plug in this value for this infinitesimally small thing. We're going to plug in just a small value to approximate this. So delta y is actual change in y values. This is f of b minus f of a. These are real y values. That's the actual change in y. Plug in one number, plug in a number, subtract them. What we're saying is we're going to take the approximation and say delta y is approximately dy, which is f prime at our starting point times some dx, and we plug in a small number here. That'll give us this value, and we'll use that to estimate our change in y. Okay, so here's an example. I've got y equals x squared plus 2x. My actual delta y, my actual change in y values. I'm going from 3 to 3.1. We're literally plugging in both of those values. So that guy right there, plug in 3.1 for x. Plug in 3 for x. Subtract those two y values, you get that number. That's the actual change in y. We're too lazy to do that. The whole point of differentials is to try to avoid doing this by doing easier computations. Like if in the real world, if we actually want to know this, if we can do it, we'll just do it. The whole point of differentials is to say that that change in y, that number, we're going to approximate by doing dy equals f prime at your starting point times some small change in x. So dy here will be, well, we need f prime. What is the derivative? 2x plus 2. Just took that guy's derivative. So f prime at 3 would be 6 plus 2, 8. So dy will be 8 times, what's my change in x? 0.1. So 0.8. So the actual change in y values was 0.81. I'm approximating that by, we call this using differentials, and I got 0.8. Okay, we'll do a few more examples. So we got a spherical golf ball. This is like a real world application here. You got yourself a golf ball. The machine that the company's using tries to make the radius 5 millimeters, but that machine's not going to be perfect. There's going to be a little bit of wiggle room in how big that radius is. So there's a possible error of 0.1 millimeters. We want to figure out what's that going to do to the volume. So we could find the actual. We could say, well, if that radius is too big, if the radius was too high by 0.1 millimeters, I could find that volume. Or maybe it was small. Maybe instead of being 0.1 too big, we were actually at 4.9 millimeters. I could find that volume. I could find this volume, and I could see what are the 3 possible volumes and figure out what the biggest possible error in my volume could be. And we'll do that, like for fun, we'll do that. The whole point is we can use differentials to estimate that error with a lot less computation. So first we need the volume, the formula for volume of a sphere. Volume of a sphere, you should know, is 4/3 pi r cubed. Then differentials, we take the derivative. So dv is the derivative of v prime, times my differential in r, dr. So we take that guy's derivative, dv. We're taking the derivative with respect to r here. The 3 will come down, kill that 3. And then drop down by 1. So we get an r squared. I'm just pausing so you can look at that. By the way, notice that the derivative of volume is the formula for surface area. That's true in any shape. Your change in volume will always be your surface area. Your change in area will be your perimeter. Like the derivative of one dimension is the volume, in quotes, of the lower dimension. Excuse me. Okay, so now my error, my delta V, the error in the volume is approximately equal to what we call dV evaluated at R equals 5 millimeters and delta R or dr is 0.1 millimeters. So that would be 4 pi 5 squared, that's R, times 0.1. I could probably do this in my head, but let's get our fancy calculator out here. So 4 times pi. 5 squared, of course, is 25 times 0.1. So the error in my volume is approximately the maximum error, 31 cubic millimeters. Oops. Because this is volume. Now let's actually find what that would be. So this was my approximation. Now let's find the actual. So let's assume, we'll ignore this one. It says ignore. Let's assume that maybe our machine is making our ball bearing just a little bit too big. So I want to find the volume when we're at 5.1 and the volume at 5. So we would call this delta V. So this guy here would be 4/3 pi times 5.1 cubed minus 4/3 times pi times 5 cubed. And again, I got my fancy calculator out. Like in the real world, I would probably just find the actual here. 4/3 pi times 5.1 cubed minus times 5 cubed. So see, our approximation wasn't great, it wasn't perfect, but it's pretty good, and it's a lot less arithmetic. So 32 point, whatever, that was 31.4. This is 32.05. All right, so maybe I'll try to squeeze my 0.4 in there. (32.05 cubic millimeters). So with linear approximation, you're using one function value and the derivative to approximate the next function value. With differentials, you're using the derivative and really the equation of a tangent line. That's really what we're doing to find changes in the function value. And they're both approximations. Okay, here's another one. I think this will be the last example we'll do. Okay, and again, we'll do it both ways. We'll find the actual and we'll use differentials to approximate it. Okay, so you should pause and read this. We've got a cone with a height and a radius, but there's a little bit of wiggle room in the cone. In fact, this is just the thickness of the cone. I want to approximate that change in volume caused by the cone. So really what we're doing here is approximating the volume of the cone itself. So let me draw this out and maybe this will be clear. So the cone is empty, right? Because it's an ice cream cone. You put ice cream in it. What we're approximating is the actual, the waffle cone itself. How much volume does it take up without the hole in there? That's what we're doing. We're using differentials to approximate that volume, where this inner radius is 4 inches and the outer radius all the way out to the edge is 4.1 inches. Okay. Well, I know volume of a cone is 1/3 pi r squared h. You may not have that one memorized, but that's what pi r squared h. That's what it is. Then the differential dv. Who's changing here? R or H? That's my height. That's my radius. Who am I allowing to change? The radius. So I'm taking the derivative of V with respect to R times dr. And here, look, here's another way to think of this. I've said dV equals dV dr times dr. Look, the drs could cancel. These are not really algebraic quantities. We really can't cancel them. I'll write this prettier here. But if we pretended we could cancel these, what would you get? You would just get dV. And so let's write that out. My change in volume, my differential change in volume will be, take this guy's derivative with respect to R. H is just a constant, pi is just a constant. That 2 is going to come down front. And then drop that power down by 1, R times dr. That's my differential. Our differential is a function that has your independent variable in it and has a dr on it. So now, dV evaluated at H equals 4. Oh, I so sorry, I lied up here. H was 4. That was my height. My two different radii were 1 and 1.1. I hope I didn't confuse anyone with that. Those were the two different radii. That height was 4. H equals 4, R equals 1, and dr, my change in R is 0.1. So that'd be 2/3 times pi. H was 4, R was 1, and my dr, my change in R was 0.1. All right, so let's throw that in our fancy calculator here. 2/3 times pi times 4. I'm not going to type right times 1 times 0.1. 0.8378 cubic inches here. Now that's just an approximation, but like it took me hardly any time at all, right? Let's find the actual, the delta V. This would be actual. You're going to have homework questions that ask you to find dV and delta V. These are, you find two different Y values and you subtract them. Here you take the derivative times your change. So this would be V at R equals 1.1 minus V when R equals 1. So both of these, let's see, that would be 1/3 pi times H times 1.1 squared minus 1/3 pi H times 1 squared, using the formula for volume. And again, I'll type all this out of the calculator. I want you to see what I'm doing here. I'm lazy. I don't want to type all this stuff twice. I'm going to factor out the 4/3 pi there and multiply that by this. 1 squared of just 1. I just don't want to type the 4. I probably would have been quicker than saying all this. I didn't want to type all this stuff twice. I just factored that out. So 4/3 pi times 1.1 squared minus 1. And so it's not the same answer. This, using differentials, we just get an approximation, but it's a decent approximation. I would say that's not a great approximation there, but it's decent. Okay, let's take a look at the homework. I'll do that in the next video.